Geometry Unit 8, Section 6, Special Right Triangles. Triangle ABC is an equilateral triangle with an altitude drawn from angle B and intersecting the opposite side at point D. The three sides of the equilateral triangle each measure 8. A couple of things. An altitude of an equilateral triangle. And all an altitude has to be is it has to go from an angle to an opposite side and be perpendicular. But when it's in an equilateral triangle, it's also a median. And what a median does is a median goes to the midpoint of the opposite side. Medians don't have to be perpendicular, but it is in this case. And so that means that D is the middle of AC. And in an equilateral triangle, an altitude is not only also a median, it's also an angle bisector. So that means that it is bisecting angle B. So this line BD is an altitude because it's perpendicular. It's a median because it's going to a midpoint D, and it's an angle bisector, so it's bisecting angle B. So determine the missing side lengths and angle measures. Well, the missing side lengths, we know that is an equilateral triangle, so it's 8, 8, and this whole side is 8. But since we determined that D is the midpoint, because this is a median, that means that AD is 4 and DC is 4. The missing angle measures, we knew that this was 60, we knew this was 60, and angle B as a whole was 60 because it was an equilateral triangle, but now we're saying it was bisected because of this angle bisector, so that makes this 30 and 30. And obviously 90 and 90. So the only other length we don't have is this length BD in here. Let me call it X, length BD. Well, I could focus on the fact that I now have two right triangles. If I just look on, this right triangle here on the left side, I have a hypotenuse is 8. I have one leg that's 4, and I don't have the other leg. So let's do a little Pythagorean theorem to find that missing piece there. So the leg I don't have plus the leg I do have squared equals the hypotenuse squared. And so x squared plus 16 equals 64. X squared equals 48. And so then x equals the square root of 48. So it's not going to come out to be a nice number. It's going to have to be something in simplest radical form. And 48 has two square factors. It could be divided by 4, but it could also be divided by 16. 16 and 3, actually. So it's going to simplify down to 4 radical 3. And that's what this length is here, 4 rad 3. That's a little sloppy. Let me rewrite that a little bit there. So get rid of that x that's there and put 4 rad 3. All right, so what is this attempting to do? It's attempting to tell you about a 30, 60, 90 special right triangle. 30, 60, 90. See, all right triangles have Pythagorean theorem. We know that. But some right triangles we consider special. The 30, 60, 90 right triangle, talking about the three angles, and also the 45, 45, 90, which is not just a right triangle, but an isosceles right triangle. That's special. These are your two special right triangles. And what this little introduction was doing is it was creating a 30, 60, 90 right triangle. Because if we have an equilateral triangle, that means this angle is 60. And if I draw an altitude, that means this angle is 90. So then this angle has to be 30, because 60 and 90, the three of them add to 180, so that has to be 30. Plus, I'm telling you that in an equilateral triangle, an altitude is also an angle bisector, so 60 is bisected. But it has to be 30 also because these three angles add to 180, and this 60 and 90 and 30 have to add to 180. So that's the other reason why they have to be 30. That's really the reason why it's an angle bisector. But what's happening in a 30, 60, 90 right triangle that makes it special? The first thing is that for the 30 degrees, the opposite 30 degrees, the side that is opposite 30 degrees. Now, 30 degrees is the smallest angle out of 30, 60, 90, right? So the opposite 30 is the smallest side. But opposite 30 degrees is half the hypotenuse. Opposite 30 degrees is half the hypotenuse. And that's what 2x and x are trying to show you. And this is, again, kind of showing that opposite the 30 degrees is this 4, which is half of 8. And the reason why that's always going to happen is, again, because this was equilateral. So that meant this side did equal this side. But this altitude is also a median that's bisecting this side. So this opposite side of the equilateral triangle is always going to get cut in half. So this is always going to be half of that. And that's always opposite the 30-degree angle. So opposite 30 degrees in a 30, 60, 90 right triangle is half the hypotenuse. That's probably the most important one to remember. Then the third side is one that has a radical. And we did a little Pythagorean theorem, and if we have this and this, we could always do Pythagorean theorem to get that. That's what we talked about in the last lecture, that if you have 2 out of 3, you could get the third with Pythagorean theorem. But the shortcut, and what's nice about the shortcut is this required Pythagorean theorem, simplifying a radical. The shortcut is just whatever this smallest side is, your other leg is that with a rad 3 attached to it. So this was 4, so it had a 4 rad 3 on this leg. If this was, say, 12, well, this would be 6, and this would be 6 rad 3. And you could do Pythagorean theorem to show you that and everything like that, but that's the nice thing about once you know it's 30, 60, 90, you don't necessarily need Pythagorean theorem. You can find the other side. And say, well, I only have this. Well, I can't do Pythagorean theorem if you only have one side, but I know this is half of it, and I know this is half rad 3. So that's your 30, 60, 90. The isosceles right triangle, which has nothing to do with this one, but the isosceles right triangle is 45, 45, 90. And how do we know it's isosceles? Well, if it's 45, 45, we know that the angles opposite congruent sides are congruent. So if you have 2 angles that are the same, that means you have 2 sides that must be the same. And the special thing about the sides of an isosceles right triangle is not just that 2 of them are the same, but that the third one is whatever your side is, rad 2. And the way that works is because I know these are the same. So like my a squared plus b squared is really just x squared plus x squared. And x squared plus x squared is the same thing as 2x squared. And then what do we do at the end of the Pythagorean theorem? We do the square root. And so when I do the square root of this, well, I can't do the square root of 2, but I can do the square root of x squared. That's just x. So the shortcut here is if I know this is 7, well, this has to also be 7. I can do Pythagorean theorem, or I could just jump to the shortcut that this is going to be 7 rad 2. It's whatever my side length is, rad 2. Just like this is whatever my opposite 30 is, rad 3. So there's shortcuts because they're special right triangles, and we know that no matter how big or small a 30, 60, 90 triangle is, it's similar to this 30, 60, 90, so the sides will all have the same ratios. That's why it works for every 30, 60, 90, and that's why this works for every 45, 45, 90 because of similarity. So let's look at a couple of questions like you might see. So given information, find what we're missing. How are we doing on time? 8 minutes. Okay. Finish this up in a minute and a half. So this is 60, 60. That means this whole thing up here is 60. So this is a case of that equilateral triangle. And so this must be 30 because this is 60, 90. That has to be 30. This has to be 30. This has to be 10 because the angle's opposite. This whole thing was 10, but opposite 30 is half the hypotenuse, and this is being bisected. And this must be 5 rad 3 because that's what, the shortcut there is. Once I know opposite 30 is 5, this is that length with a rad 3 attached. So AD is 5, BD is 5, rad 3. Ugly, but I'll move on. Okay, how about this one? Well, this is 60, this is 90. That means this must be 30. And all I have is opposite 30. Well, I know opposite 30 is half the hypotenuse, so that means the hypotenuse must be 14. And opposite the 60 is the same thing as opposite 30, but with a rad 3 attached. So 7 rad 3. And once I have these, I could do Pythagorean theorem and simplify the radical, but that's much quicker. All right, 45, 45, 90. Well, I know it's 45, 90, so this has to be another 45 because they add to 180. And so if this is 5, this must be 5 because it's isosceles. And the shortcut is my hypotenuse is that rad 2. So ij is 5 and hj is 5 rad 2. Okay, one more. 45, 90, so this has to be 45. And I'm looking for both of these sides. And I give you the hypotenuse. But this is where students tend to get stumped on the 45, 45, 90 because they say, wait a minute, isn't this supposed to be something rad 2? Well, maybe it is. Maybe these are radicals. And a radical times rad 2 kind of thing. So you'll see. So what we could do is if we really get stumped, since we know these are the same, we can do Pythagorean theorem here that I know my two legs squared equals the hypotenuse squared. So that's 2x squared equals 144. So this is really the one case where you could do Pythagorean theorem with only one side because you know the other two sides are the same because it's isosceles because 45, 45. And so x squared equals, I can divide by 2, 72. And then simplifying rad 72, just to save time, that is 36 times 2, so 6 radical 2. And so that's what both of these are, 6 radical 2. And you'll see why, if my side has rad 2 in it, my hypotenuse is my side rad 2. So it'd be 6 rad 2 with another rad 2. And rad 2 times rad 2 is just 2 times 6 is 12. So for 45, 45, 90, whatever your sides are, your hypotenuse is that rad 2. But if your side happens to have a rad 2, you'll see the hypotenuse doesn't because rad 2 times rad 2. So these are your special right triangles, and they are basically shortcuts to Pythagorean theorem, but these triangles come up a lot throughout the year, and we're going to see them again in the next trig chapter. But remember some key things, like opposite 30 is half the hypotenuse, isosceles, the hypotenuse is the side rad 2, things like that, and you're going to have to work with some radicals here and there. And that's it. All right, see you.